Okay, we made it back. Friday, it's the end of the week, at least the end of our week. There might be more stuff that you're trying to get done for today, this afternoon. And really, there's only one last like concept that we're trying to get through in this homework, and then repeat some math a couple of times, like rinse, dry, repeat, plug in numbers, and then move on from there. So when, let's see. It is due today, is that right? Here we'll get into our logistic work. Spring, no, we're in fall 24. 2120 calendar, and then due date. So goal is wrap up homework 2, get some answers, and then submit our work. Oh. Cool, we can do that. We can get this done. So we were kind of talking about like the motion and how you can describe like constraints using vectors, about how if we're connecting vectors to each other, then we can write out how those vectors have to add up, and once those equal signs are there, whether it's equal to 0 or it's equal to one vector equals another, and that's just fixed. We can use that to start building out what equations we're trying to solve for. So in this case, where we have this last part, these last 2 parts, so we'll call this like point A, O, B, and C. So O doesn't move anywhere, C doesn't move anywhere. O connects to A connects to B connects to C in this kind of system. Start drawing our vectors in there. I like to do this one. Oh. This vector is RA. This one, what is this one if it's connecting B and A like that? Yeah, RB with respect to A. Nice. What about going from C to B? What is that one? What is that one? What's that vector called? Going from C to B, so that like the fixed point up to B. These arms, like in general, for this like 4-bar linkage, this one is the crank arm, moves around in a circle, at least most of the time, right? For a lot of 4-bar. So A goes in a circle, and then B rocks back and forth. So here's the rocker arm, here's the crank arm, and then connecting the two. So rocker, crank, and then we need a super cool name for that middle one. What do you think we came up with for that? The one that connects the things. Because we're really creative as engineers, so we probably came up with something like awesome, like it's a connector. Yeah, connector rod. Because so we have like crank arm, rocker arm, and then connector connects the two to each other. So you get rotating motion turns into reciprocal motion. Kind of cool. Well, very cool, actually. Not just kind of cool. Okay, so what's our rocker arm vector? What is that one called? All that was just to get you. Going from C up to B. Yep. RBC. Yep. B/C. And then this one down here, I'll call that one like RC. So how do I add these vectors together to set up a constraint equation? How do I want to do that? Or how do you want to do that? I have these vectors of points that are moving. What are the constraints on points A, B? I guess mostly A and B, because those are the moving points. O and C are they're fixed. So what kind of constraint did you come up with? Or can you come up with? Yeah. Yeah, you drew RB. Yeah. And then what would that tell you for what's the constraint on RB? Yep. Yeah. And what was like the vector conditions? And then what it was that RC is so you could think about it that way. Okay. Okay. Yeah. Yeah. Okay. So this came up twice so far, thinking like what about this vector, right? Of describing where is point B when this thing's moving around. Like A moves in the circle, B is moving left and right. What is RB? So what I could say is that RB is, if I move up along RA and then out along RBA, so I could make that statement that in order to get to point B, I have to go up along the crank and then along the connector. But another way to get there is RC plus R of BC. And both of them have to stop in the same location. That's good, because now I can get rid of that. Because this vector RB, I don't really know anything about. Like if that angle or that distance changes, it's not something that I can like measure or control because it's not directly connected to any rigid bodies. It's just like something describing that position. But I can take these two and say RA plus RBA equals RC plus RBC. Nice. That's good. That means that we have all 3 points all connected to each other. So I have a constraint. And if I have a vector constraint, do you know how many constraints that puts on? 3? What's the, yeah. Oh yeah, because there's also like planar. So here, if we're saying that everything is planar motion, then we're creating like 3 constraints on it to say like everything moves just in that plane. But you're right. Like if you're also saying that that there's an X, Y, and Z constraint on it for 3-dimensional motion, then you'd have 3. And if it's just planar, then you consider like 2 components. Do you see what he's saying, or what we're saying as a collective? Like every time you have an equation that says this has to equal that, it becomes a constraint on motion, and it reduces your degrees of freedom. That gets dropped. I'm gonna rearrange some stuff. What about velocity A, velocity BC? How are those? Do we have a constraint on that one? This is my what would the velocity look like? Same like vector equations. Well, what does that one look like? Well, the constraints wouldn't have, like gravity is not a constraint. Gravity creates a force. So constraints are always like just connections. This angle has to be some fraction of that angle, or these 2 parts have to move together. So yeah. Yeah, so usually like gravity, because it's a force, creates is a cause of motion rather than a constraint on motion. To be like extra. Yeah. Wouldn't the value of that velocity equation be the same as the position equation? Just like the velocity instead of position, the velocity is just saying, just take the exact same R values and plug in V values like that. Do I know anything about those velocities? VA, VBC. Oh wait, I wrote BC twice, didn't I? This should say BA. My bad. Do I know anything about BA, BC, VC? I do know some stuff about it, but something zero. There's one of these terms is zero. C? Yeah, VC. I can get rid of that and say that those three velocities have to add up to zero. Because point C is always a constant value, so its derivative has to be zero. It just makes the velocity constraint like a little simpler. But I find it easier to add up positions and then find velocity rather than trying to figure out relative velocity terms. There's other ways you can get here if you're like, this guy is crazy, I'm going to do it my own way. Go for it. Totally rederive it your way. I'm all for it, and I'll help you any way I can. All right, so then let's start plugging in some things that we know. I keep copying this thing down, so I have it here. So like RA is going to be the length of that first link times cosine theta 1 in the I plus sine theta 1 in that J. So I have the total like distance away from the origin for A has to be link 1. Like it's got to be equal to that link length. And then the direction is going to be whatever this angle, whatever this theta happens to be. And I'll call this one like a theta 2 and a theta 3. Good. Let's start off with just one at a time. There's definitely a pattern to it, so if we can figure out one, we can figure out the rest, because they all look kind of similar, right? So what is, if this is my position of A, what is the velocity of A? It's got to be like a derivative, right? Some kind of the change in A per time. But what does that look like in terms of theta and L1? And then sines and cosines. So theta, L1, sines, cosines. What does that velocity look like? Yeah. Yeah, so you can like map your way through it. All right, I'm gonna start taking derivatives. Yeah, yeah. Yeah, and I and J are constant too. The direction that can go up and down. Yeah. Yeah, derivative cosine is negative sine.
So this is usually what I see. But I saw someone that didn't have this, which made me very happy. But this is usually what I see when people go to take a derivative. Yeah.
I took like the derivative with theta and multiplied it by that.
Ooh, and then multiply this whole thing by d theta 1 dt. Yeah. Why'd you do that?
Because theta is not.
Yeah, theta is changing. So when I'm trying to take the change in this function, the function is a function of theta, but theta is a function of time. So I need to use this, like, this is the fancy way of using chain rule. And every semester I say, this is a chain rule. And people are like, that's not the chain rule. You're crazy. I think it gets taught a slightly different way. But there's all sorts of ways of teaching chain rule. So like dRA dt is dRA d theta times d theta dt.
So we can drop in a dr d theta and then multiply by d theta dt.
Nice. Love it. You guys killing it. So I'm gonna bump this whole thing over so that I can say this is a theta 1 dot.
And this is like so if something is moving in a circle, the farther away it is from the center of the circle, the faster it moves. And that's what that L1 and theta dot are. The bigger the crank arm and the faster it rotates, the bigger the magnitude of velocity. And those sines and cosines are just telling you where it's pointed along that direction.
Cool. Now we've got we have a pattern here. Theta 2 dot, negative sine, theta 2.
And I have everything that I need to plug into all of my like constraint equations and figure out how to solve for one thing given something else.
Where did this guy come from? Left over.
So what I want to do now is take just the I components and set them all equal to 0. So if I add up all the x directions, they all add up to 0. And if I add up all the all the heights, they all have to add up to 0.
Might as well copy this one down. All right, so what do those two equations look like for like VA plus VBA minus VBC. What's that? What are those equations? No. Yeah. Yeah, I know. It's a lot of numbers. For the project, we'll do it all Python. Same process, but all Python. And make sure it's not writing it out the whole thing. Just so now we have we're taking that vector equation and turning it into the scalar equation. So all the x and all the y and that way we've got two equations with three unknowns, but we know one of them. So we were trying to find like what are theta dot terms, like what are the theta 1.10, how fast is that theta 2 moving? But yeah, if you write out positions, then you can always theta 2. Have you used that dot notation before? Have you seen that? Like put dots on stuff? Okay. Is anyone? It's okay if you haven't. Like I saw some head nods, but the dot is just the shorthand way of showing d over dt. So so if I want to say like theta dot, it's saying d theta dt. It's helpful, especially in dynamics where there's so many like moving parts and different variables. So the dots tell you like, okay, this is a time derivative of the same variable, rather than having like extra fractions kind of thrown in there, which can be a little confusing. All right, L1 theta 1 dot sine theta, L2 theta 2 dot sine theta 2 minus L3 theta 3 dot sine theta 3. Ran out of room. And I ran out of room. Should have shrunk the stuff that I was keeping track of. Yeah.
For the x component, shouldn't it be negative, and then positive? Because for the x component, it's negative.
Yeah, I could write negative, negative, positive, but it's all equal to 0 anyway. So if I multiply by -1,
Okay.
it's still 0. It's like whether you add then subtract or subtract then add, it all ends up. It still has to satisfy the same thing, that the total delta between the two minuses and the plus, it's got to be 0. And like we did all this math, but really like you could have thought of this as like like if you look at just the y components, h1 and h2, that is L1 sine theta plus L2 cosine theta, and then h3 is L3 cosine theta. So h3 has to be h2 plus h1, otherwise something's broken. Like we've broken our constraints on the original problem. And now we have these two equations. With two equations, how many unknowns can we have? Two. How many unknowns do we have right now? What do we know? 4, 3. Let's check out, like, because now we've gone through, like, we created two equations for this. This is true for any 4-bar linkage. Like, we have a specific one in a specific location, like in a configuration, but this, you could use this for anything that has 3 moving bars that are all pinned in 2 locations. So let's start identifying what do we know. We know where points O, A, B, and C are, which means we should know something about those angles. We might not know them directly, but there should be like geometric information, like they have to be certain angles in order for this thing to be true. And then we know that link 1 is spinning in a circle at 10 radians per second. So I know, let's put in another equation. Theta 1 is 10 radians per second. And then let's map out. So if this is R0, then RA is negative 0.2, positive 0.14, somewhere up here. And then RB is 0.5 and 0.86, so somewhere like over here. And then point C is 1 and 0, so 1 unit over and 0. Where was this? 0 0.49, 0 0.9, 0 0.5, 0 0.9, and negative 0.2. So we have like constraints that are geometric things to tell us what those angles are and what the sines and cosines are, right? Because we also know this is 1 meter, that's 1 meter, and this is 0.25 meters. So I know the hypotenuse for each one of these sines and cosines. So what is sine theta 1 and cosine theta 1? I know it's something over 0.25. What's the something? Like we have these different x, y conditions, right? Is it going to have anything to do with any of these two? Let's see if we do. Yeah. The sine theta and the x value or the y value. Yeah, exactly. Oh, it already has such a right angle, right? What do you mean? Oh, you mean solving for like theta 1 minus 180? Like just this angle? Oh, okay. Yeah. So you're thinking of like that angle, right? That you use this one. Okay, that would work. Yeah. Yeah, in this case, sine of both of those are the same, but cosine is negative. Yeah. Part of the reason that I walk through this is like figure out like where are we at, like what's going on, and so we had a nice discussion about like how are you supposed to find the sine and cosine when it's not like when your angle is so big, right? Like how am I supposed to work with that? Because normally we think of it as like here's your right triangle, right? Here's theta. This is my adjacent. There's my opposite. There's my hypotenuse, and then I can do SOHCAHTOA and have like this is where the angles are. But this is the same process even when we think about it in terms of like bigger angles like this. You can have a negative adjacent, like a negative A over here, over in quadrant number 2, when the angle is more than 90 degrees. And then we would have like a positive, sorry, I keep writing hypotenuse there, positive opposite, positive O. And as long as we're just using, and this is partly personal preference, but also it makes your life a little easier. If you're always measuring angles from the x-axis, then it's always the same like sines and cosines. You don't have to keep flipping directions or like changing a sine to a cosine or a cosine to sine. And that's how we end up with these curves of like for theta going from 0 to 360, sine goes up, comes down and then back up. Cosine is the exact same thing, but just shifted over by 90 degrees, right? Or wait, shifted over this way. There we go. Sine and cosine are just sine theta plus pi over 2. So when I'm looking at this, when I have actual coordinates for that sine of theta 1, I can plug that directly in and say this is negative 0.2 and this is positive 0.14. And I don't have to worry about what is that is the angle in quadrant 1, quadrant 2. Like I already have the stuff that I need. Now we get to the trickier ones. Well, at least I think they're a little trickier. So we have to think about this triangle and this triangle. Thinking about where those are for sine theta and cosine theta. Nice. Yeah. Take the relative positions, right? Yeah. Yep. Yeah. 0.5 minus that negative 0.2. Okay. Nice. Waiting, hoping that it's all right. It's all of roots. All of this is wrong. Every single thing up there is just completely wrong. No? Okay, where do you do that?
Doing
Which map?
the final.
Okay, yeah. And relative. Okay, yep. Yeah, it's all the same height, right? All right, so we had the right track for the most part. Like in this sine, when I'm looking at theta 2, describing that triangle, I don't want this total height from 0 up to b. I just want this little height, just from here to here, which is a relative. So like b minus a. So it would be that 0.9 minus 0.14 all over 1, and then here that 0.5 minus a negative 0.2 all over 1. And then same thought process for that sine theta 3, cosine theta 3. So sine 0.9 minus 0 over 1, and then 0.5, but here it's negative, right? Like 0.25 minus that 0.5, something like that. And check the round off errors. I rounded off so I'm not writing as many numbers, but now everywhere I see a sine theta 1, I can plug in negative 0.2 over point. Is it 0.5? L1? I think L1, yeah, L1 is given as like 0.25. Or which one?
So that just says horizontal BC.
Oh, down here? The 0.25? Sorry, it'll catch up in a second.
Yeah.
That one? That one I'm getting from, like I'm just trying to measure this from here to here.
So that's just 0.5 minus 1.
Negative 0.5. Yeah, that would help. Yeah, I'm subtracting the wrong thing. See, I told you, it's all wrong. Everything's wrong. And I'll take that sine theta 2, 0.76, I think you said. Sine theta 3, 0.9 over 1. Cosine theta 1, 0.14 over 0.25. Theta 2, 0.7 over 1. And then theta 3. Now I've got a negative 0.5 over 1. Yeah.
So if sine is opposite over hypotenuse, why for sine of theta 1 would you do?
Oh, did I use the adjacent? 0.2. I did use adjacent because everything is wrong in here. Did I do that? I only did it for the sine, right? For theta 1?
I think it's just, yeah, just the,
All right.
so those are just
Yeah. Yeah, the reason is because I'm doing it in front of an audience, and therefore you have to make mistakes. But not because that's the way it's supposed to be done, just because it is a mistake. Time flies, huh, when we're having fun doing math. So we are out of time. Can we spend, would it hurt anyone's feelings to not finish this right now and come back Monday and finish? Right, yeah, move deadline, extend deadline to Monday, and then we'll just finish up on Monday. Let's do that. All right. No one's feelings are hurt. If you want to turn it in now, bueno, but if not, we got time. Oh, I'll stop recording so we don't